I was working on a project once where I was trying to do a automation series on YouTube in my spare time, and I came to find out that despite the fact that I don't really think of myself as having a life, I really, turns out, don't have much spare time either. Hello, welcome to Chaos and Controls, a show where we talk about modern devices, technologies, and techniques for automating your home, business, or life. I'm your host, the Automation Doctor. So, I'm going to admit today's going to be a fairly simple one, but I thought maybe we could go ahead and talk a little bit about the fundamentals of digital or boolean logic. Now, many of you have probably encountered what a boolean statement looks like in the wild, or at the very least can reason through one, even if you don't explicitly understand that what you are looking at is an expression for digital logic, or boolean. And as it turns out, in all of logic, not just digital logic, but certainly it is much more prevalent, there are three key words that you really want to hone in on when looking at a statement. And those are and, or, and not. So for an example, let's assume that maybe I've got a fancy garage door that I'm trying to put in, and I've got a little wireless signal that it can use. But let's say it also, maybe I have a camera system outside that I can train to recognize faces. Facial recognition, at least in the civilian market's fairly easy to fool, even with just a printer that can make somebody's likeness. So maybe a code that goes along with it too. So I have to both have a system that recognizes you and you have a code. And so I could say that the garage door will open if you have the clicker-clacker, or that the system recognizes you and you have a code. And of course, I could make the logical inversion to that statement by saying that the garage door will not open if you do not have a code, or the system doesn't recognize you, and you do not have a clicky-clacker. And that would be a very simple but easy to understand use of your basic and or not clauses. And as it turns out, most of programming in general ultimately, fundamentally, comes back to these three key words. So let's go ahead and derive what are known as the truth tables for each of those statements. We'll start with the not statement because it is functionally the easiest. If I have a single input, A, then the output from that circuit is said to be A naught. And on the truth table, if A is a 0, A naught is a 1. If A is a 1, A naught is a 0. Easy. Similarly, for the AND statement, you can see here I now have two inputs, A and B. And I will only have a logical output of 1, or true, or yes, or however I am mapping my zeros and my ones, if both A and B are a 1. Otherwise, it fails the check, and we have a 0, or false. Lastly, the OR statement, A or B, for my inputs on the truth table. If I have either one of these, I get a 1 over here, and if I have both of them, because I do have one or the other. There is such a thing as an exclusive OR, where they cannot be equal to one another, but we don't need that for this particular example. You can still fundamentally build all of logic out of these three statements, and, or, and not. Now, I said this was going to be a simple one today, so that's about all I have for you. You guys have a good one, and I will catch you next time.